All right, let's start. So first of all, you may have noticed the poll for the homework and project report extension. So please vote your opinion by the end of this week. It's by the end of this Sunday, so that we can collect all the votes and make decision on Monday. So looks like the poll so far says that I mean most most of you want an extension for that. Okay, well, we're totally fine on that. Okay. And another thing is regarding the online exam. So I said on Tuesday that we're gonna have an online exam, and the date is on April 24th from 10:30 to 12:30, 10:30 a.m. to 12:30 p.m. So it's kind of exactly the schedule done by the university at the beginning of the semester. The only thing changed is that we're gonna take the online exam rather than stay in some classroom and have paper exams. The benefit is that you won't need to derive a lot of mathematical stuffs because of those physical constraints. So I believe the exam content will be easier than previous semesters. Okay, anything regarding the homework and also the final exam schedule?
Uh, so you posted an announcement saying that we should vote, but I didn't see a link to where we can vote. Where is the link to
There's a
that?
survey. There is the quiz. There's a quiz on Canvas.
Oh, okay, thanks.
Yeah, just like at the very beginning, we have made a survey to look at your interest, your background, such kind of things. We made kind of similar survey. So you just take a look at the survey. It is a informal quiz, but it's not quiz. It's just survey. Other question? And we still have, after today's lecture, we still have one more lecture on next Tuesday, I believe. For the last lecture, the plan is here. We're gonna first do a brief review of our class throughout this semester. So please take care of those review. It might strongly relate to we're gonna you will see in our final exam. And then we'll introduce some practical concerns and suggestions of using machine learning. So the basic is kind of a review, and so it's relaxed lectures, not very intensive and very, demanding. Okay. So yeah, let us start with our lecture. So today we're going to talk about another Bayesian learning method. It's called naive Bayes classifier. Sorry. Okay, so we're going to first introduce the definition of naive Bayes classifier. We're going to highlight the difference between the naive Bayes classifier modeling and logistic regression. So we actually briefly mentioned in the last lecture, right, where we focused on logistic regression. In logistic regression, we are interested to model the mapping from input and a probability of label being one, right? So we actually use a conditional model. So we model what is the likely or what is the chance that your label y is one given x. So in our probabilistic model, we never care about how x are generated, right? Maybe how those input features are generated. We call this type of model as discriminative model. Why we don't care about the input, we only care about output given the inputs. That's why it's called discriminative or conditional, right? From naive Bayes classifier, you see that actually in our joint modeling, we not only care about given x how we predict y, but also how X are sampled. Right? So it's actually joint probability or joint probability distribution rather than just the conditional distribution. So this type of model is called generative models. But modern Bayesian, I mean, about 20 years ago, it's kind of hot topic to discuss the pros and constraints of generative models and conditional or discriminative models. But now their gap is kind of vanishing. People are trying to build up a model which is so complicated, including both the generative component and the discriminative component, and then train that model with a lot of data. And this is the trend. This is the trend of the frontier research right now. But just give you a sense what is the idea of these two types of models. So we're going to first introduce the definition of the naive Bayes classifier, and also and then we'll. Sorry, I have to move the and also we'll talk about the learning algorithm of the naive classifier. Okay, so first word about naive Bayes classifier. Right? So basically, as we just mentioned, right? So it is a model which characterize the training data with a joint probability, so P of X and Y. So let us first use Bayes rule to predict Y given input X, right? So this kind of conditional probability or posterior probability, right? To calculate this posterior probability of label being Y for a particular input X, we can use Bayes rule, right? So we first compute the joint probability. Right? The joint probability can be decomposed as the prior probability of big Y, the label Y equals to the specific label, multiplying with the conditional probability that given this particular label, X, the specific input feature vector X is produced, right? And this is the joint probability. Then we divide the joint probability with the marginal probability of your feature value X, right? So yeah, this is just a review of Bayes rule, right? So, and for the prediction, right, we're not just suppose you're doing discrete classification. You have several classes, right? We want to give you a particular label, right? So how can we do that? We're going to maximize this posterior probability. We predict the label who has the maximum posterior probability, right? So that means we can get the probability by maximizing this definition based on Bayes rule, right? And of course, the denominator is the marginal probability of X, right? It has nothing to do with Y. It does, and it is positive. It's also is always positive, right? So we can just discard it. That means our prediction amounts to find the maximal value, which maximizes the prior of your label, multiplying with the conditional probability of your input features given this specific label, right? So any questions so far? Okay, looks like it's pretty straightforward for everybody. Okay, so but don't confuse this with map learning. So this is talking about how you, given a specific model, right? Given a probability model to describe the relationship between your input and the label, and how, according to this probability model, to make the prediction. This has nothing to do with the notion of Bayesian learning we mentioned before. Like we mentioned that we can place a prior over the entire hypothesis space, right? Where for each particular hypothesis, we assign a probability density. And for each subset of hypothesis space or subregion, we assign probability measure. But anyway, that notion mentions and defines how we're going to search over the hypothesis space according to some probability definition, right? So this is talking about like given a particular probability model on your training data, how we find, how we make prediction of the particular label. So we can see that if we use a joint probability to define our model, right? So the prediction then is doing with two components. The first component is the prior probability of the label being this specific y, right? And the second component is the likelihood that the likelihood of the observed features. Be careful. We're talking about likelihood of observed features, not label, given this label y. So suppose you have like 3 labels, right? You have 1, 2, 3, or 0, 1, 2, whatever. So if you want to select which label is your prediction, we're gonna look at the product. This product for each choice of label, say py equals 0, multiplying the likelihood of x, observed input vector x, given the label is 0, right? So this is the first value or product you need to look at. And then you need to compare that with another product in which your label is 1, right? P of y is label 1, multiplying with the likelihood of the observation, input features observation given your label is 1, right? And then you compare with the third case where y equals to 3, y equals to 2, right? And then you just look at the 3 products values and which one is the largest. You're going to use the corresponding label as your final prediction, right? So this is very different from logistic regression. If you do logistic regression, okay, there's nothing, there's no component here, right? We do not care about how given different label the input features are generated. Right? We just give a conditional model p of y given x. So in other words, if we use this strategy or idea to make prediction, we need 2 sets of probabilities, right? So first set of probabilities is that what is the prior probability for your label taking different values, right? And second set of probabilities about likelihood, right? So given different label, what are the parameters to determine the likelihood of the input features, right? So let us see a concrete example, right? So we go back to the tennis playing example again, right? So which we have used to talk about decision tree learning, right? So if we do not look at all the examples or just collectively look at them, we'll see that without any other information, the proportion of we finally decide to play tennis is 0.3 and staying at home is 0.7. Right? All of it, we can get this prior probability, right? Suppose y is a label that you whether play tennis or not. This is a binary label. So the probability of y equals to 1 is 0.3, and the probability of y equals to 0 is 0.7, right? And then to get the set of probabilities that can determine the likelihood, we can take a look at the data, right? So on one day, on days that I do play the tennis, right? What is probability that the temperature is T and wind is W, right? So right now we just look at observation, which consists of 2 variables, temperature and wind, right? So when we look at the table of the observations, we see that okay, when playing tennis is yes, we can calculate the probability that the temperature is hot and wind is strong is 0.15, right? Hot and weak 0.4, cold and strong 0.1, and cold weak 0.35, right? So now I have the first set of probability, right? But we also need to talk about, we now also need to look at when I do not go to play tennis, I just stay at home, what is the probability for specific combinations of temperature and wind, right? So here are another set of probabilities. So if those are all our input features right now, if we are given a particular combination of temperature wind, we can follow this definition to calculate the product of the prior and likelihood given specific label, and then find out the best decision, right, whether I'm gonna play tennis or not, right? So yeah, so the input will be, okay, the temperature is hot, this is one example, right? And the wind is weak, right? So I want to decide, I want to predict whether I should play tennis or not. So I just multiply the prior of play, multiplying with the likelihood that given your play or not playing, your temperature is hot and your wind is weak, right? So we can calculate that. So first, if you choose to play tennis outside, that means this label is yes, right? So we multiply the prior that you play, and then given you play, what is the probability of hot temperature and weak wind, right? So just read the table. So the prior of playing is the prior playing is here, right? 0.3 here. And then given you play outside, so we should look at this table, right? Your temperature is hot and your wind is weak, 0.4, right? So multiply them together, you end up with 0.12. And this is a score that when you choose to play outside, right? So what about the score that you decide to stay at home, right? So first, the prior that you stay at home is, according to this table, 0.7. Then we should look at, given you stay at home, you do not play, what is the chance that temperature is hot and wind is weak? Right? So we should look at the table here, right? So your temperature is hot, your wind is weak, so we can say it corresponds to the second row. So the conditional probability is 0.1, right? So now you multiply 0.1 with 0.7, you end up with 0.07. So now which decision or which prediction should I make? Any idea? Any suggestion?
I would suggest taking the highest probability.
Yes, right? This is our rule, right? Our prediction rule. We want to find out the maximum posterior probability given the data, the label, right? So to do that, we need to maximize the joint probability, that is the prior of the label, and then the conditional probability given the label, what is the observed features, right? So by computing the joint probabilities for two choices of the labels, we say, okay, when you choose to play tennis outside, you have a larger joint probability. That means you have larger posterior probability, because posterior probability and joint probability are just the difference is only a factor, right? A constant factor. So from this calculation, we can immediately do the prediction. That is, yes, we're gonna go outside to play tennis. Okay? So this is the idea of the naive Bayes. So basically, what is naive Bayes? I'm gonna the framework is that I'm gonna model the joint probability of your label and the input vectors or input features, and then in the prediction, I'm gonna predict with the label who has the largest posterior probability, right? So, but we do not actually need to calculate the exact posterior probability. We just need to maximize the product of the prior and the likelihood, right? So now let us look at more realistic problem, right? So we make decision based on a model. We have only 2 features. That is the temperature and wind, right? But what if we have 4 features, right? This is the original example. We talk about the decision tree construction, right? So we have the outlook feature, the temperature feature, the humidity feature, and wind feature, right? So outlook feature has 3 possible values. Temperature has 3, humidity has 3, and wind has 2, right? So, and as we mentioned, right, before we make prediction, we first need to know, okay, what is the prior probability when you make decision for different decisions, right? What is prior, whether you play or not, and then what is the likelihood given a particular label, the observed feature vector, right? So let us first look at the prior, right? If you want to determine the prior, we only need one single number, y.
We can calculate the opposite probability by doing 1 minus the single number.
Yeah, exactly, right? Because this is just a binary prediction problem, right? So the prior is either you do it or you not do it. If you know the chance that you do it, you just you get the chance to not do it by subtracting 1 with that probability, right? So now the issue is the parameters we need to estimate to determine the likelihood. So as we mentioned, we need to know on each specific label, what is the likelihood of the input feature, right? So we know that our feature vector consists of 4 features, right? So that means for each particular value of a label, 1 or minus 1, we need a value for each possible assignment. P of feature 1 taken x1, feature 2 taken x2, feature 3 taken x3, and feature 4 taken x4, right? So now I'll ask how many numbers we need to determine those probabilities or likelihoods.
Is it 36?
I'm not
3 times 3 times 2 times 2?
Yes, right. It's very good. So we know that for this outlook feature, we have 3 possible values, right? For the what does this mean? Sorry, I need to look at H. What does it? Oh, temperature. Okay, sorry. So for temperature features, we have 3 possible values. For humidity feature, we have 3, and wind, we have 2. So if you multiply them together, it's 3, 3, 3, 2, right? So it's
54.
Yeah, 54. But as we mentioned, right, because you only need 53 values, right? Because the probability that you choose the very last combination can be obtained by subtracting 1 with all the previous all the other probabilities, right? So actually, just 53 parameters in each case, right? And then for playing decision, you have you need to determine 53 parameters, and for not playing decision, you need to determine another 53 parameters. One parameter determines a specific combination, right? But how many examples do we have?
Just the 14.
Yeah, we have just 14, but we need to estimate more than 100 parameters out of 14 examples, right? So it's too hard, right? It's really hard, and you can imagine, because when the more the parameters you have, the more likely your model is overcomplicated and overfit training data, right? So in this case, it's typical that your model parameters are even more than the number of samples, right? So if so, this is a big problem, right? If we think about the case in general, right? Suppose we're doing multi-class classification. That means we have k labels. Well, k labels, that means, okay, we need k minus 1 parameters to determine the prior probability, right? Because the probability, the summation of the probabilities taking each of those labels will be 1, right? So you only need k minus 1 parameters. The last parameter is just obtained by subtracting 1 with the summation of the other probabilities, right? So then let us take a look at the likelihood. How many parameters do we need to determine the likelihood? For simplicity, we just assume, okay, we have d features, but each feature is just balloon, either 0 or 1, right? So then we can calculate how many features do we, how many numbers do we need to determine each probability, right? So we know first we have k possible labels, right? So for each particular label, we need the parameters to determine this specific conditional probability, right? And we have d features together. Each feature can take 2 possible cases. So how many combinations do we have in total of the values?
To the d.
Yeah, 2 to the power of d, right? But of course, because this is a kind of multinomial probability, right? So to determine the probability, you take each specific combination of x1 to xd values. You only need 2 to the power of d minus 1 parameters. Why? Because the very last, the probability you take one specific combination is obtained by 1 minus the summation of the probability you take all the remaining remaining combinations, right? So in total, we have a k labels. So for each particular label, you have this 2 to the d powers, 2 to the power of d minus 1 parameters. For k cases, you should multiply them together, right? Any question? Okay, so I assume this is kind of straightforward to everybody. Okay, so now we can say the number of parameters actually grows exponentially to the number of features, right? So that means, okay, I need a lot of data to estimate those many numbers, right? And also, every time you increase one more feature, you double you at least double the number of parameters, right? So it's kind of crazy. That means, okay, the model complexity is too high, right? It's very easy to have your model parameters much bigger than the number of training examples. So it's very easy to overfit. Now how can we address this problem? Any idea? Any brainstorming? Any thought? No thought? Okay, so the idea is relatively naive. That's why it's called naive Bayes. So now that estimating the full joint conditional probability, I mean this one, right? Given y, is kind of very expensive because the parameter space is too large. I'm gonna restrict the form of this, right? By restricting the specific form of this conditional probability, we can largely reduce the parameter space. Then the question is, how can we, what kind of simplification can we make to simplify this conditional probability, right? So the naive Bayes chooses the independent assumption. So what is the independent assumption? So basically, it assumes that given y, the joint probability of x1 to xd is equal to the product of the conditional probability of each feature given y. So to give the detail, we can let us first review the definition of conditional independence, right? So suppose we have three random variables, x, y, z are random variables. Right? So we say x is conditionally independent of y given z if the probability distribution of x is independent of the value y when z is observed or given. So basically, you can write it in this form, right? So the conditional probability of x given y and z it is equal to conditional probability of x given z. If you just remove y from this conditional probability, it doesn't change the, it's just change the value, right? Another common use definition is written like this, right? So the joint conditional probability, P of xy given z, is equal to P of x given z and P of y given z. And this is conditional probability, conditional independent, right? So as we just mentioned, like even for the binary features, if you want to model the full probability P of xy to xd given y, we need k to the power k times 2 to the power of d minus 1 parameters, right? Is a large number of parameters, right? So to simplify this form, what if all the features were conditionally independent given the label, right? This is called naive Bayes assumption. So if you write it down, it basically says, okay, P of x1 to xd given y equals to P of x1 given y multiplying with P of x2 given y multiplying blah 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 until P of xd given y, right? So this is actually a definition of conditional independency, right? Given y, all those d features are assumed to be independent of each other. So this is a key assumption of naive Bayes, and and it is the key reason why naive Bayes is practical, right? So now let us look at how many parameters do we need to determine these conditional independent probabilities. Right? So first, for each particular conditional probability, say P of x1 given y, how many parameters do we need to determine this conditional probability? Any idea?
2.
2? Just 2? Only 2? Yeah, we can think about it. So first, well, here we just assume x1 to xd are all binary, right? So if you just look at the conditional probability of x1 given y, so how many values does x1 can take?
If they are binary, just 2 values.
Yes, just 2 values, right? But as we mentioned, if you want to determine a distribution over a random variable having 2 values, how many numbers do you need? If you want to determine a binary probability, right?
Just 1?
Yes, just 1, right? Because you either take 1 or 0, right? If you know the chance of 1 is 0.6, okay, the chance of 0 is just 0.4, right? Just subtract 1 with that chance. So now we can say for each particular feature, right, the corresponding conditional probability is only determined by one parameter, right? So we have D features, right? So how many features do we have? Do we need in total?
D.
Yeah, D features, right? So this is for one particular choice of label Y, right? So suppose we have K labels, then in total we only need KD parameters, right? Yeah, someone asked, should we be worried about numerical instability here? So that's a very good question. So we'll talk about later in the learning of the naive Bayes. So basically, yeah, people are trying to smooth the calculation of probability in the case that some account of the features are so sparse. Okay, so so let us continue, right? So now we can say by assuming this naive Bayes independence, right? Conditional independence. The number of parameters now is reduced to KD parameters, which are proportional to both the number of the features and the number of labels. So it's not too bad. Although if you have a huge amount of features, the number of parameters is still large, but it's much better than this one, right? So now we come to the formal definition of naive Bayes classifier. Our assumption is that the key assumption is that the features are conditionally independent given the label Y. Right? So to make a prediction, we need to learn or estimate two sets of probabilities. First is the prior of the label Y. Right? Secondly, are about the conditional probabilities for features. For each particular feature xj, what is the likelihood P of xj given Y? Right? So once we have these two sets of probabilities in hand, we can make a prediction for a new feature vector, right? So how can we make a prediction? We just make map prediction. We maximize the product of the prior and the likelihood of all the D features given the label. So according to the conditional independent assumption, so the likelihood is equal to the product of the likelihood of each feature, each individual feature, right? Okay, so now I have introduced the definition of naive Bayes classifier. Any questions so far regarding definition?
Is there any drawback to our assumption of the conditional independence?
Is any what?
Drawbacks? We are assuming conditional independence.
Yeah, of course, definitely. There must be some drawback on that, right? So basically, in many real-world applications, you'll say, okay, the features are not conditionally independent, right? Like temperature and whether raining or whether snowing has strong relationship, right? If it is snowing, then the temperature won't be high, right? It won't be 80 degrees, right? It won't be 100 degrees, right? Obviously, it does have some kind of strong relationship or correlations between the features. So ideally speaking, it's not a valid assumption. But in practice, people found that, okay, this kind of bold, naive assumption often gives you a really good performance.
So when we are assuming conditional independence when there is not, are we overestimating the probabilities? Is that right?
It's not gonna like overestimating. It's just give you an inaccurate estimation. You can view that, okay, here are a set of data, right? Here are a set of data. I give you an inaccurate model to fit that data. And I just test that model, and okay, in practice, found the performance is really good. But that does not necessarily mean your model is correct. Actually, your model violates some basic facts of inside data.
Thanks.
Yeah, but there are some kind of approaches or some kind of methods to alleviate such kind of strong assumption. Like I can pick up a small subset of features which I believe have strong correlations. Then I just model their conditional probabilities jointly. But compared with other set of the remaining features, I assume, okay, those subset of features, say 4 features, 5 features, are still conditionally independent with others. But inside those 4 or 5 features, we model their joint probability. This is another common use way to trade off in between, right? You need to reduce the computational cost and model estimation difficulty. You need to make some kind of sacrifice, right? You cannot assume, okay, the model is so expressive and so flexible to include every case, but if you simplify your assumption too much, it may deviate the ground truth too far away, right? So I'm gonna make some kind of trade-off in between. Okay, very good question. So now let us proceed to the learning of the naive Bayes classifier, right? So here I'm gonna explain the learning in a Bayesian learning framework, right? So remember the notion we mentioned, the Bayesian learning framework. We define a probability over the hypothesis space, right? So then we're gonna search the hypothesis who has the largest probability, right? So if we take a look at the naive Bayes model, first we need to look at how is the hypothesis H is defined, right? So actually the hypothesis can be viewed as a vector, which consists of a collection of the probabilities. So for a particular hypothesis, right, it must include the prior for each label, right? And the remaining part of that hypothesis includes the likelihood for each particular feature xg given label, namely p of xg given y, right? So you can imagine each particular hypothesis is a vector consists of all those values. So your hypothesis space are set of all possible such kind of vectors, right? We're gonna search over this hypothesis space. We'll identify a particular hypothesis. We identify the corresponding prior and likelihood terms. With that, we can do whatever prediction we want, right? So this is the definition of hypothesis and hypothesis space, right? And suppose we have a data set with m examples, right? So for convenience, we have we point out some notation. Sorry, I want to change it to laser point to be more clear. Okay, so we denote examples with some subscript. The xi means that ith example, and because each input vector is a vector, right? It consists of say quite a few features. So we denote the jth feature in the ith input example by xij. So we add one more subscript j to index the feature in that vector, right? And of course, and also we use Italian to denote a particular scalar of the feature value, right? So this bolded Italian just shows this vector. So don't confuse that as notation. So now from the notion of Bayesian learning, right? If we have a data set D with m examples, and I want to learn the classifier in a probabilistic way, what is the probabilistic criterion to select hypothesis, right? We have mentioned 2 strategies, right? MAP and MLE, right? So MAP means that, okay, I assign some prior distribution over the hypothesis space, or H here, right? So this prior encodes my prior beliefs over which set of H has larger chance to be the ground truth, which are not, right? And then we have some likelihood that given this particular H, we can calculate the joint probability of the data set. So now let us just assume we don't have any prior preferences over any hypothesis. We assume they're uniform, then our probabilistic criterion reduces to the maximum likelihood estimation. Right? That is, we just search over the hypothesis space and take a look at possible H, and we find out the specific H who maximize the joint probability of the data, D. Right? Again, H is defined by all the probabilities used to construct naive Bayes decision. Any questions so far? Okay, I assume this is everybody is satisfactory at this point because this is important. This is important for us to understand the framework. Okay. So as we mentioned, like the data set with M example is really assumed to be independent and identical distributed, right? So P of D given H is further written as a product of P of each pair of example, each pair of the input and output label given our hypothesis, right? So, and then next we need to know what is the probability would this particular H assign to the pair of xi, yi, right? This is something we have just defined, right? So then this probability of a particular pair of input feature vector xi and label yi can be further decomposed as the p of yi given H. And then the conditional probability of the input vector, the feature vector given yi, and given its hypothesis, right? So according to our naive Bayes assumption, namely the input features are conditionally independent given the label, right? So we can further written this likelihood as a product of the likelihood for each particular feature, xij, right? As we mentioned, xij is the jth feature of the ith input vector or input feature vector, right? So now we have our objective, learning objective, right? So we need to find out the best hypothesis H by maximizing this learning objective, which is essentially the joint probability of your data, of your training data, right? And how do we proceed? Do we just do this maximization?
Take a log.
Yes, exactly right. This is the same idea we do for the logistic regression, because this is a probability between 0 and 1. This is probability between 0 and 1. You have a lot of features. You multiply a lot of small values together, and it's very likely that finally you end up with a number close to 0, and due to some numerical issues, it might simply truncate to be 0. Right? We can do nothing about optimization. So in practice, to ensure numerical stability, we usually take log, right? Because if you take a log, it doesn't affect your maximization results, right? But you don't need to suffer from the numerical issues. So when we take a log, then the product becomes a summation, right? So you're gonna sum over the M training examples where each summand will be log of the product yi given this particular hypothesis plus the summation. Again, this is over all the training examples and over every feature, the log probability of each particular feature value given yi and under this hypothesis. Right? So now let us take a look, how do we do this maximization, right? So in general, we need to make modeling assumption about the functional form of this probability distributions, right? We just talk about, we talk about if xij, those features and also labels are all discrete, right? So now I want to ask, if we're thinking about the binary features and binary labels, what is the form of those probabilities? An idea? If we assume, okay, our features and labels are all binary, what is the form of this P of xij given yiH and P of yi given h?
The second sum only has two indices,
Yeah.
and one of them is 1 minus the second one.
Yeah. But then what kind of probability or distribution you can use?
Binomial?
Yes, exactly right. Just the standard distribution, right? If you have two values, that means your binary variable, the most commonly used distribution is just Bernoulli, right? Or binomial, yeah. So suppose there are two labels, 1 and 0, and all features are binary. So of course, to determine the prior, we just need one parameter denoted by p, right? P of y equals to 1 is the small p, and p of y equals 0 is then 1 minus p, right? And the likelihood for each binary feature given the label, we can denote it by aj, right? So when y equals to 1, so that means we parameterize this probability p of xj equals to 1 given the label is 1 by aj and 1 minus aj, right? But this is not enough because we have two possible labels, right? We need to consider the case when y is 0, right? So we denote the parameters determining the parameters for the conditional probability when y equals to 0 by bg and 1 minus bg, right? So given those parameters, we can use the Bernoulli, the binomial distribution to model those probabilities, right? So here, the hypothesis, right? Those things, right? Those h which are conditioned on, actually is a long vector. You can assume it's a long vector which is comprised of those p values and all the a's and b's. Okay. So let us first look at the prior, right? So we know we use p to denote, to parameterize this prior probability, and we're going to use the particular distribution for this binary prior is a Bernoulli or binomial distribution, right? So the form of the binomial is like this, right? So p to the power of indicator yi equals to 1 multiplying with 1 minus p to the power of indicator yi equals to 0. So this square bracket is an indicator function. So when the condition inside this indication function is true, then the indicator is 1, right? Otherwise, the indicator is 0, right? This is called indicator function. So you can see whenever it actually gives you a unified form of this probability, right? When y equals to 1, well, this part is deactivated, right? So you have this probability to be p. When y equals to 0, this part is deactivated, right? So you have this probability 1 minus p. So similarly, for the conditional probability of each binary feature, given the particular label yi, we can write down its probability form in this way, right? So this actually summarizes all the cases when yi equals to 1, when yi equals to 0, right? In the case of yi equals to 1, this is a binomial distribution form, right? So it is to the power of xij equals to 1 or 1 minus aj to the power of xij equals to 0, right? Similar form applies to the case when yi equals to 0, right? So from this unified form, you can obtain the probability for any choice of xij and yi. Does it make sense? Okay, if you have taken some statistical courses before, like introductory courses to statistics or introductory courses to probability, I'm sure you have done such kind of practices before. It's just a high school competition, right? So now we just substitute this form for P of Xij given YH and substitute this form for P of Yi given H. And then we maximize this objective with respect to the parameters P and parameters AIs and BIs, AJs and BJs, right? So then you just calculate the gradient, right? Set the gradient to be 0. You can end up with the optimal values of the parameters, right? So I'm not gonna derive them. It's basic. Everybody can do that, right? So first, I just give you the conclusion, right? So first, the P, the optimal P, is computed by just counting among your training data how many labels are 1 divided by the total number of the examples. That is the count yi equals to 1, count yi equals to 0. It's just the portion of the positive examples. And similarly, you can compute AJs. Remember, AJ index the probability of a particular J's feature equals to 1 given your label is 1, right? So this is just the optimal value is the count of yi equals to 1, xij equals to 1, divided by the count of yi equals to 1. So this is just among the portion of xij equal to 1 in the examples who are positive. It's quite intuitive. So similarly, bj, the optimal bj turns out to be the portion of the examples where xij equals to 1 in the negative examples. That is yi equals to 0, right? So when you implement your own naive classifier, actually you never need to manually derive those formulas and then substitute those forms into your objective, right? And take the gradient and set 0. You just count, right? Just have a counting table and count how many positive examples, how many negative examples, how many xij equals to 1 in the positive part, and how many xij equals to 1 in the negative part, and divide them. That's it. So now let us look at a concrete case. So, so first, given our 14 examples, right? So we want to learn naive Bayes classifier on all of these 14 examples. First, we need to determine the probability of the priors, right? So we have a this is a binary classification, right? So we have 2 labels. So we need to determine what is the probability that you play outside in the prior. So we have 14 examples in total. We just count how many positive examples in these 14 examples, right? So we have 9 examples, right? So according to the formula here, right? So we just divide the number of positive examples in total, which is 9, over the total number of the examples, right? The size of training data, which is 9 over 14, right? And then we can immediately obtain that the prior probability that you do not play is 5 over 14. You just subtract 1 by this positive probability. And next, let us look at the conditional probability for each particular feature, right? So first, we're going to look at, okay, given the label is positive, what is the probability that the outlook is summic, right? O equals to S. Then we should look at what kind of subtable. An idea?
Subset of all with positive labels.
Yes, exactly, right? So as we mentioned, right, this is just counting, right? So it is conditional on the case that the label is positive. So we're gonna narrow our look in a subset of examples who is just positive, right? So we know that, okay, there are in total 9 positive examples, and from those 9 positive examples, we're gonna look at how many examples are summing. So it turns out to be 2, right? Only these 2 examples are summing in these positive training examples. So our conditional probability is 2/9, right? So similarly, the conditional probability of outlook is raining given the positive example will be 3/9 because across these 9 examples, 3 of them have the outlook feature to be raining, right? So the remaining thing is clear, right? So we only have 3 possible values for outlook feature. So the probability O equals to S is 2/9, O equals to R given positive 3/9. So the remaining part you even do not need to count. It's just 1 subtracted by 2/9 subtracted by 3/9, which is 4/9, right? This is consistent with our observation. Among 9 positive examples, we have 4 observations, right? It's 4/9. So similarly, we need to take a look at the cases, the conditional probability of the outlook features given negative example, right? So the computation is pretty similar, right? You just look at the remaining portion, right? Negative examples and count how many examples have the outlook to be sunny, to be rainy, and to be, what does this look like? Overcast, yeah, it's overcast, and then you get probability, right? So then you go on to calculate or estimate the probability of the temperature feature given you play or you not play, the humidity feature given you play or not play, and wind feature given you play or not play. Then you can get all the necessary probabilities, right? And then finally, you can have all the thing you have, and then you can do whatever prediction you want, right? Any questions so far? No question? Okay, going back to the question someone asked before, right? And someone asked whether we have some numerical issue, right? So here, I just gonna give you a hint because you're now required to implement naive Bayes because of our tight schedule of the class, right? So, but just to give you a hint, in practice, simply just, count how many positive examples, how many negative examples, those kind of things are not sufficient because of the data sparsity issue. So it is possible that given some kind of label, say positive, you don't have any outlook feature to be, say, overcast. In such kind of cases, what can you do? Can you just give this conditional probability, say, to be 0? Like, let me repeat this question again, right? So suppose now if I take a look at negative examples, right? I want to calculate P of the outlook is overcast given your play is negative, right? You do not play. And when I look at the subtable where the play is negative, I do not find any feature values of the outlook is overcast. From the formula we just mentioned, this conditional probability is simply 0. So now I'll ask, can we just use 0? Any idea? No thought? Well,
We can have a threshold for 0, something like 1 to 10 to the -6, for example, something like this.
okay, yeah, that's very
Using
good
star
point.
0.
Yeah, that's very good point. Yeah. So the first, you have realized that if you simply set the conditional probability to be 0, remember when we do the prediction, right? When we do the prediction, we're gonna choose the label yi. Sorry, I should go back even a little bit. Yeah, we have to choose the label y who has maximized this product, right? So if you have some unfortunately, if unfortunately your test example has such particular observation, right? We'll calculate the conditional probability of y equals to say negative, then you have some 0 value inside the product, right? And we know that if you multiply whatever with 0 is just 0, right? So of course, you don't want to see that. So one possible solution is to, okay, I'm not going to directly set it to be 0. I will set it to a very, very small value, like 10 to -6 or 10 to -3, and then so that I can give a reasonable value and compare that with other choices of the label, right? And another commonly used metric. So this is a very good point, right? But here I want to tell you another commonly used trick is to add some pseudo count to ensure there is no 0 at all. Right? So how can I add a pseudo count? I can just assume I can add the count of features by 1 for every example. And then when I do the division, there will always be some non-zero denominator. So to take an example, right? So we assume the count of yi equals to 1, xij equals to 1 is always 1. Right? It's not always 1. It's something like this plus 1. So in the denominator, we just add the total actual count. So see that? So how many examples do we see here, and how many total numbers of actual count is added in the denominator? That means even you have a 0 of this count, you have an actual 1 here, right? And you have non-zero actual count in the denominator, so you have non-zero value. So this technique is called smoothing. Any questions so far?
You just add 1 to the denominator, or add many number of 1s to the denominator?
You just add 1. Just
1
add
to
1. Oh, you mean the denominator?
Yes, yes.
It depends, but usually you won't add both. Oh yeah, the most common case is that you add 1 on both numerator and denominator. Right. So we have a say you have 1, you have 3 really count, right? Real count, and you have 8 total count. So when you use this trick, you add both numerator and denominator by 1. So your result will end up with 4 over 9 rather than 3 over 8. This is one approach. Another approach is that, okay, now that I add a pseudo count 1 here, right? And then the denominator, I'm gonna add the total number of pseudo counts for all the cases. So then that won't be 1, that will be like, so we have like 2 combinations. So here it will be 2.
Okay.
Does it make sense?
Yes.
So basically, there are a lot of smoothing techniques to address this, to tackle this data sparsity issue, because in real world, you often see the case, right? For some particular count, simply 0, right? We cannot make it to be 0. We need to add some pseudo count, and yeah, just to give you a hint. Right? Any questions so far? Okay, great. So we have finished the introduction of naive Bayes. Hopefully that gives you a better sense about the probabilistic learning and how this is conducted, right? So our assumption, so for naive Bayes, the learning, although can be is originally derived by maximize the drawn probability, and then to get 2 sets of probabilities. One set of probabilities determines the labels, right? The prior of labels. The other set determines the likelihood, right? But actually, the learning is just to count, because the optimal results is obtained by counting how often features occur with each label, and then we just normalize them to get likelihoods. And similarly, the priors is obtained by taking a look at a fraction of examples with each label. And those learning procedure naturally generalized to multi-class. So it's the same thing, right? And then once we have got these 2 set of probabilities, we can use our model to make prediction. So remember, the prediction is a map prediction. We're gonna find the label who maximize the product of the prior of label, and then the likelihood of the data given the particular label, right? So this is actually your score is product of 2 parts. One is prior, one is likelihood. Then you find the label who has the highest score. So the key assumption underlying naive Bayes is the conditional independent assumption. That is, all features are independent of each other given a label. Okay. So without the assumption, the consequences are severe. You cannot deal with a very large number of features, because the search space, the parameter space, will grow in an exponential way, right? So only when you induce this independent assumption, you can largely reduce parameters. But as some student just asked, yeah, it will oversimplify model, especially when your model assumption largely deviates the fact inside in the model, right? So the learning procedure from the Bayesian learning notion is kind of maximal likelihood learning, because each hypothesis is a vector, consists of all the necessary probabilities to determine a specific naive Bayes classifier, right? You're actually searching those vectors who give you the best probability of the data, joint probability of the data, right? So of course, in our derivation, we just assume, okay, we do not have any prior preferences over those hypothesis vectors. But of course, you can try, you can add your own prior over that, and such that your learning is to maximize the prior of the hypothesis space, multiplying with the likelihood or the probability of data given a particular hypothesis. And the idea of the naive Bayes also generalizes to real value functions, real value features. So what you need to do is just to determine what kind of probability of the feature value given the label, right? So a commonly used probability distribution will be the Gaussian distribution, right? You just need to determine, okay, what is mean, what is variance? You ask them from the data. That's it. Or kind of mix of the discrete features and real value features. For discrete features, you can use multinomial distribution, right? And for real value features, you can use Gaussian. And sometimes you can choose other distribution as well, like T distribution, whatever, right? But in general, naive can you can use whatever feature types and integrate into naive framework. And particular interesting stuff about naive is that the prediction is done also by maximum A posterior. So you can say map estimation is applied in different levels, right? The learning principle and also in the prediction, right? So we need to find the label who has the largest posterior probability, in other words, or equivalent largest joint probability, and this also generalized to beyond binary classification. You can use that to do the regression as well, right? Okay, so any question?
In map approach, we need to add a regularizer.
Yeah, it is equivalent to adding a regularizer, right?
And what should be the regularizer here?
You mean the prediction?
No, just the regularizer term for optimization. For example, we had 1/2 WTW in logistic regression, but here that was our regularizer. Here, what is instead?
No, here the learning procedure doesn't have any regularizer. The learning is just to maximize the joint probability of data. So the joint probability includes the prior of the label multiplying the likelihood of data given the label, right? So it was just trying to maximize this. So that's why we call it maximum likelihood learning. If you want to add some prior over hypothesis, yeah, you can add one more regularizer, like your half H transpose H can be your regularizer. But here we just choose H to be uniformly distributed. We don't have any prior preferences over H. Does it make sense?
Yes, but then what's the difference between map and ML here?
MLE here is just mean, okay, how you find hypothesis, right? The hypothesis is a vector. This vector consists of all the necessary probabilities to determine a naive base, right? But here we do not, you can see that this is our learning objective, right? So given a particular hypothesis, we can determine the likelihood of data, the joint probability of the data, right? So just maximize this. We do not add a prior over H. If you add a prior over H, then it is map.
Yes. If we want to a prior over H, what should be the prior?
You can have whatever prior you want. But H is a vector of the probabilities, right? It's between 0 and 1. You better put some prior distribution over values in between 0 and 1, right? Like beta distribution, right? Like Dirichlet distribution, whatever.
Okay.
Any other question? Okay, great. I'm stop here, and next Tuesday will be our last lecture. So hopefully, even we decided to even if we decide to extend our homework and project report, please start to do it as soon as possible, because you guys all have other deadlines and courses and finals, right? So don't hurry up at the last minute. Okay, see you.